Okay, so hello everyone. Today we'll start to talk about application of heat transfer in the science and technology field. So we have a lot of applications related to heat transfer. That's why we did a small review on the main heat transfer principles. I will broadly talk first about these different applications, and then we'll do some practical problems to remember how to use these equations. So to start with, the first sector, if you want, that will use a lot concepts on heat and mass transfer is the construction and building sector. So whenever we want to design a building, we need, if you want to make it energy efficient, we want to reduce as much as possible interaction with the surrounding, because during summer we have relatively much higher temperature outside, and during winter much lower temperature outside. So we need to protect our indoor environment from the external one. That's why we work a lot on the design of our building, and we have a lot of strategies that we can talk about. One of the main strategies is to select appropriate construction materials and layers to reduce, if you want, the heat transfer from the outer to inner environment. So if I consider, let's say, the outer side, okay, in general, the interaction between the external envelope and the outer side will be through two types of heat transfer. Convection and radiation. So let us consider, for example, during summer. During summer, we'll have heat that can go inside the envelope through convection. And as we have seen in the revision, convection is related to the motion of a fluid over a surface. So you have continuously air is blowing over your surface, and this convection can be natural if you have relatively small velocities of air, or can be forced in case you have wind at high velocities. So we can give you the condition at outdoor. So of course, when you design your building, you study the climate over the whole year. You can determine critical times for T infinity, and you can get the values of your convective coefficient with outer environment. And you have, of course, radiation. So you can calculate also, depending on the outer weather conditions, what is the value of Q radiation. And we'll do together an example in detail about how we can model radiation between the sky and our surface, the surface of our envelope, the outer surface. Now, if we consider a steady state case, so whenever I say steady state, this means that no variation with time. We can consider that this heat will will be transferred through the envelope by conduction, because our envelope, let's say, is made of several solids, and we can divide it into several layers, A, B, and C. So if you just look at buildings in construction, you can realize that they can put several layers. In general, we have, let's say, bricks, and in between have, guys, please, if you don't ask question, just mute your microphones. Okay? Can you please mute your microphone? I think it's Rida.
100%.
Rida, can you please mute your microphone?
Sorry.
Okay. So we have several layers, okay? And the selection of type of material depends on the insulation desired, okay? So, and this insulation desired also is, of course, affected by the climate. So if you have extreme climate conditions, you need a better insulation. While in moderate climates, you can compromise between the cost, because higher the insulation, higher the cost of your material. And as we said in this course, we'll try to compromise between energy efficiency and cost. That's why we'll do an economical analysis for the project and alternatives that we are suggesting. So in moderate climate, you can compromise a little bit the quality of your envelope. You can have lower resistance for your envelope because you don't have very large variation in temperature between inner and outer space. So this will allow you to reduce the cost of the material you are using in your envelope. And then after, let's say you have 3 layers of solid, and within these layers, heat is transferred by conduction. Then heat will then be transferred to the inner space, and also it can be a combination of convection and radiation, or only convection, depending on the case. So depending on the scenario, if you want that is proposed, sometimes maybe they will tell you you just have convection, so radiation can be neglected compared to convection. Okay. Then in this case, to be able to study the effect of your envelope, you need to develop a mathematical model which will allow you to solve for the temperatures at different nodes of your system by a simple method. Okay. So first, you just have to first say, I want to write like an energy balance for my system. And what is the energy balance here? How we can write the energy balance in this problem? What do we mean by energy balance?
The energy in and out.
Exactly. So I can take, very good. If I take first, let's say a very thin layer over the external surface, okay? I can say, since I have conservation of energy through this layer, okay? And since this layer is of negligible mass, no storage, no generation, I always have for a thin layer sum of Qn, sum of Q dot n equal to sum of Q dot out. So the rates of energy coming in equals to the rates of energy getting out. And this will allow me to say that Q radiation from side 1 plus Q convection from side 1 is equal to Q conducted in material A, okay, at x equals 0, let's say. But here, because it's a steady state case, I don't have storage or generation, let's say, in my envelope, then I can consider that for each layer of my envelope, Q conduction entering material, a certain material, is equal to Q conduction exiting this material. That's why we can talk about one flux of conduction, if you want, through your envelope. So this is equal to Q conduction within the envelope, because we consider steady state case without storage or generation, equals to, at the end, to Q convected from the outer side, from the inner side, sorry. So Q convected to the inner side, Q convection to, and to develop a technique that will allow us to solve for temperature variation without a lot of complexity. And here we can write the equation of temperature in A, B, and C. But we need to make things simple. We need to simplify things. So if we observe, if you want, this problem, we can do an analogy with electricity, because what is happening, heat is transferred from outer to inner environment through first convection and radiation, then it will move by conduction, and finally by convection. And the flux, so the flux is equal from the beginning to the end. So this is very similar, if you want, to electrical system. How it's similar? If I consider, for example, an electrical circuit, okay? In electrical circuit, I can measure the intensity by just the difference between voltage. So I have voltage at point 1, I have voltage at point 2, and I have a certain resistance. The, the current that will go through my system can be written as I equal to the difference in voltage over the resistance. And how is it, can this be comparable to heat transfer? If I just focus first on convection. So in my problem, first, let us say I have Q that is coming in through two ways. The first way is by convection. So I have a convective flux entering my envelope. I can call it Q convection. And in parallel, because I am adding two fluxes, you know that in case of electricity, in case you have resistances in parallel, you add the intensities. And here's the same. In case heat transfer is divided into two parts, it's equivalent if you want to two heat rates coming in parallel. So I have Q convection going through a resistance to convection first, and this Q convection is added to Q radiation through a resistance in parallel. And these two fluxes of convection and radiation will be added together to be transferred through the envelope by conduction. So I can represent my thermal system or my heat transfer system by an electrical circuit using electrical analogy. So when they will be added together, they will move through the envelope by conduction, okay? So I have now a total, the summation of these two from the energy balance, Q convection 1 plus Q radiation 1 will move through the envelope by Q conduction. And of course, the material of my envelope will resist to this heat transfer by developing a certain resistance to conduction that we will see how to get. And finally, if I have here several layers, let's say A, B, C, you can divide your resistance to three parts. Resistance to conduction in material A, resistance to conduction in material B, so R conduction in B, and finally R conduction in material C. And then you will reach the end of your envelope, okay? At end of your envelope, you have the inner temperature, T inner. So here we have T inner if you want. Here we have T, at this node, you have T outer. And here you have, let's say for convection, you are having convection with T infinity 1. While for radiation, for example, let's say you consider radiation with the sky. So I can give you the temperature of sky TS, T sky. Okay. And finally, to the inner side, whenever your flux will go to the inner side, it will go through convection process. So at the end of your circuit, you can just put resistance to convection. Okay. And here, the temperature will be T infinity 2. So we can deduce that energy transfer can be determined by analogy with electrical systems. Okay, and by doing this figure, you can simplify on yourself calculation of your temperatures, because all you have to do then is to say that I can, for example, in case let's say you have that T sky can be simulated by a value close to T infinity 1, for example. okay, to simplify the model. Then you will have here one temperature node. So let us consider that we have here one temperature node, T infinity 1. You can say, I can calculate the heat rate going through my system by just doing delta T from the beginning to the end. So delta T over the whole resistance of this electrical system, or here it's a thermal system, yani over total resistance, or total. And you know from electricity how to calculate the total resistance. You have that for parallel resistances, okay? You can do, let's say, R1. So we know from electricity that R equivalent for two resistances in parallel is equal to R1 times R2 over R1 plus R2. Okay. And we know that if we have several resistances in series, all we have to do is to sum them. Okay. So by this way, by doing this simple model, you can calculate the heat rates through your envelope. And your purpose is to minimize this rate because you want to isolate the external and the inner environment. So here you can develop through science and technology, you can develop new materials that will allow you to reduce this heat transfer between the inner and outer environment. And therefore you need to rely in a lower amount on heating and ventilation systems. So you will have more energy efficient use of your building. So whenever you select appropriate material in your construction, you can reach very high energy efficiencies, and then you can reduce your electrical bill, you can reduce use of ventilation systems, etc. So this is one of the main application of heat transfer. We need to understand the concepts to appropriately design our envelope. And not only we talk about the design of the external envelope of our building. You know that through windows we'll have a lot of solar radiation that will come in. So we need to understand, let's say, property of radiation, absorptivity, reflectivity, transmissivity, okay, that we introduced in the introduction to heat transfer. In this way, you hear a lot about, for example, difference between single glazing and double glazing. So why we need to put double glazing windows? Because also this will help into reducing the heat transfer between the inner and outer side. Sometimes windows can be of positive role. We want heat to be transferred to the inner environment, which is the case, for example, during winter. During winter, we need to benefit from sunny hours to heat our space. This is why we need to optimize the orientation of the building in a way to absorb more sun during winter and less energy from the sun during summer. That's why we study, if you want, the relative direction of the sun in order to know during winter what are the facades exposed to sun. And we put on these facades large glazing ratio, while for facades that are subjected to the sun during summer, we try to minimize the presence of windows and the total glazing area. Okay, so from here, the importance of relating our basic knowledge of heat transfer to applications in the energy field. Any question on this before we move to discussion of another application? Okay, if you remember, when we talked about energy, we said that we need to tackle several aspects, energy transfer. And this is an example of energy transfer, how energy is transferred through different modes of heat, convection, radiation, and conduction. But also we said that another important aspect is thermal storage. So what are the different types of thermal storage? How we can optimize the storage to also reduce the energy consumption of buildings, etc. So here we talk about, if you want phase change material. If you are talking in the thermal sector, we talk about phase change material, we talk about thermal mass. And if we are talking, let's say, in completely different application, if you are talking in the field of cars, we can talk about storage of energy through batteries. So some of you suggested to work on topics related to battery design, how to different charging method for batteries of electrical vehicles or hybrid vehicles, etc. So if we go to the transport sector, it's more electrical. If we work in the heat sector, we need to talk about phase change material or about thermal mass. And in both cases, we need to know the basic relations of heat transfer. And if, for example, if I talk about thermal mass, okay, again, going back to our design of a building, we already discussed envelope and windows and how this is related to heat transfer. We can also discuss thermal storage. So for example, in general, in buildings, you can put high thermal storage at floor level. Or also we discussed one application, but of course this will require large space, water walls. And you can put, let's say, in big hotels, water walls that can absorb heat during the day and release it during the night. So the basic, if you want, equation will rely on how heat is stored. We know that heat is stored, can be stored through latent or sensible form. That's why now in the next chapter, which is chapter 2, we'll consider both cases. What is Q sensible? So when heat is stored with change in temperature, okay, and we have a formula for Q sensible equal to MCP delta T. And in this case, you know that what we try to do to store more, okay, without affecting the inner space, you need to put a massive thermal mass here. Why? Because you don't want this thermal mass to have a big change in temperature. It should store heat while having a very low increase in temperature to not affect, to not having overheating of your space. Okay, so this is why it's suggested to use a massive material, high mass and high specific heat. That's why for a certain value of Q sensible that is absorbed, you will have a small variation in temperature of your material. So let's say if you walk on the floor, you will not feel a high raise in temperature for the floor. But this floor, this massive floor, will store heat when you have excess of heat absorbed by your environment. So during the day, let's say during summer, we have a high number of sunny hours, so heat will be dissipated within the space. Of course, if you study well your envelope and you put high insulation, you will reduce this amount. But still, you have a certain flux that will come in your space. And this flux that will come in your space will lead to overheating of your space in case you don't implement other strategies. Or you should put an HVAC system that will work on electricity. But of course, we need to reduce this because in general, to produce electricity, we might go to fossil fuel because we use generators. So this is bad for environment. So we need to come up with passive strategies. This means that we don't rely on energy from external sources like fossil fuels. Of course, if you use renewable energy to operate the HVAC system, it will be good because we are using a free source that is renewable. It's fine. But still, we can try to reduce because we know that for renewable energy also, we cannot ensure it the whole time. So we need to help it. We need to have backup strategies that are passive and at the same time that they reduce the they increase the energy efficiency by reducing the amount of electrical energy required. So here, what will happen is that if we use appropriate thermal storage with high mass and high specific heat, we can store this excess of energy during the day. And when needed, it will release it back to the inner environment. So during the night, when you have drop in temperature, this will work especially in regions where you have high differences in temperature between the day and the night. So if we talk about the Bekaa region, for example, this will be very efficient because you have very high temperature, average temperature during day and relatively low temperature during night. So during the night, your thermal mass will restore back the energy stored in order to keep the temperature within your environment acceptable, and it will fluctuate in a very reasonable range. Okay, while if you don't have good construction for your envelope and appropriate thermal mass used, then the temperature profile will fluctuate a lot, and this will lead to between day and night, and this will lead to a high discomfort of occupants, and then you need to rely a lot on your HVAC system. So here also, to design appropriately the thermal mass, we need to start from a basic equation of heat transfer, which is that the sensible heat stored is mCp delta T. And then depending on the amount of heat that will come in your environment, you can do appropriate design for what is the mass needed in order to allow you to have a stable temperature in your inner environment. Another material that we can be used, as we mentioned before, is PCM, phase change material. It can be used in construction. It can be used in a lot of other applications. In cooling vest, for example, you know that workers will feel a hot sensation when working. So they need, if they put appropriate clothes or what we call, let's say, a certain cooling vest, this vest will help to keep them in comfort. What is the concept? We are implementing in this vest PCM, phase change material. So let's say you have the vest and you implement within the vest several encapsulated, if you want, package that contain PCM. And of course, you need to select the PCM in an appropriate way. And the temperature of change in phase should be within the range of temperature the workers are working in. Okay, let us say you have an external environment temperature of 40 degrees, which is very hot. You can select a material that can perform change of phase at this temperature. And then at the initial state, your PCM will be in the solid state. And as you have the workers doing their job, they will feel high temperature outside. So in order to evacuate heat from their body, this jacket will absorb this heat. And the PCM material will take this heat to, if you want, change in phase from solid to liquid. Okay, and as long as you have the two phases at the same time, this will allow you to absorb heat without increasing temperature, okay, of your PCM. And then once you reach the complete liquid state, we say we reached saturation. So the vest will not be efficient anymore, okay, because it will not be able to absorb heat from your body. And in this case, you will start to feel hot sensation. That's why, in general, we study what is the amount of PCMs that we should put to cover the number of working hours, the normal number of working hours. And in this way, we can ensure that as long as the worker is doing his job, the PCM will be in the phase of a change of phase. It will not reach saturation, because once we reach saturation, the vest is not efficient anymore. So we can, depending on the working condition, design appropriate PCM with corresponding temperature of phase change. And we decide on the amount of PCMs that we should put depending on the working condition. So this will be based on a very simple relation, which is that the heat absorbed by PCM, Q latent, is equal to the mass of PCM that I am using times the latent heat, which is a characteristic of the PCM, and what will represent, if you want, what is the amount of energy released when I go from solid, absorbed, sorry, when I go from solid to liquid. So this will be in joule or kilojoule per kilogram. Okay, so depending on the material, each PCM is characterized by a certain latent heat of fusion that will be given, let's say. And depending on the amount of heat that we, if you want, we predict to be released by the worker, we can design an appropriate cooling jacket. We can talk about the same thing for construction materials. Sometimes within the construction materials, they implement PCM because PCM will help into absorbing heat without having to increase the temperature of the envelope. And this will help to reduce heat transfer from the outer side to the inner side. So whenever we talk about energy storage field, it's very wide.
Professor?
Yes?
The latent heat who will HFG?
Exactly, yes. In some books, they call it HFG. Exactly, yes.
Okay.
Okay. So depending on the book, you can have several names. So just you need to know, if I tell you the heat, the latent heat of fusion or the latent heat of evaporation is in kilojoule per kilogram is of that amount, you just have to multiply it by the mass to get your absorbed heat in joule or kilojoule. Okay. Any other question on
Okay,
that?
thank you.
Welcome. Okay. So so we have seen applications for sensible and latent heat. We have seen application for different modes of heat transfer, including convection, conduction, radiation. Other applications that are very important in energy and science technology sector is heat exchangers. Okay, you will find heat exchangers in a high number of very high number of applications. Let us talk first, for example, about solar systems. So whenever we'll talk about solar energy, we'll see different types of solar system. We already talked about PV panels. We already talked about concentrator systems. Okay, we can consider, let's say, if you want one basic technology of solar system relying on the following. So we have, let's say, your panel. Okay, you have your PV panels that is exposed to the sun. If we talk about PV, it's photovoltaic cells. So we need to talk about a technology that will rely on how to transfer solar or thermal energy directly to electricity. So, and then we'll go into electrical details. Let me give another example because we need to focus now on heat transfer. If you need to consider one mode, if you want, of heat exchange, you want to trap solar energy, okay, and then to use the solar energy for heating purposes. And you can use it, let's say, to ensure domestic hot water needs. Okay, one of the possible heat exchangers will have the following simple design. You have, let's say, a tube in a cylindrical form. Okay, the outer side of the tube is exposed to the sun. So it will absorb, let's say, heat by radiation and convection, as we have seen in the previous example. And this heat will go through first the tube by conduction, because here you have a solid material. Okay, so it's very if you want, similar to the envelope example. So you have first heat getting in, within the solid material of your tube. Of course, you will select the material of tubes for your heat exchanger should be of high conductivity in order to facilitate heat transfer from the outer environment to a certain refrigerant. And in general, in such system, we can circulate water within the inner cylinder. Okay, so whenever you circulate, let's say, water or any other refrigerant inside the tube, this fluid will capture the energy transmitted, the solar energy transmitted through your tube, and it will be convected by the fluid. And then you can have, if you want, this water that will pass through the heat exchanger will be heated, and it can be circulated, let's say, through a system for heat distribution. And you can store it. If you don't need it now, you can store it in a tank. And whenever you need to have a shower or whenever you need domestic hot water, you just have to pass it through the distribution system in order to be used by people. Okay, so this very simple example can be designed in can open questions for several ways to design. First, let's say, what is the best material to use? Maybe you can say to increase the amount of heat absorbed, I can use we use sometimes some if you want thin glass layers. These glass layers that are added will help into trapping in a better way the solar energy. Okay, so if you want, you can study the structure of your heat exchanger. What are the different layers that should be used? If we use glass, a certain glass thickness, how it can improve the amount of energy absorbed. Okay, so we can study by considering different scenarios. What will change, if you want, is the overall resistance. Here you will try to reduce resistance in the opposite of envelope. In envelope of your building, you need to protect your inner environment. So you need to increase the resistance to heat flux. While in heat exchanger application, it's exactly the opposite. You need to absorb the maximum energy from the outer environment. So you need to select material with good conduction properties. You can put several layers. We will see together that we have what we call concentrated tubes, where they put also glass layers that will enhance the heat transfer to the refrigerant. And this refrigerant can be distributed to cover your needs. Plus, we can talk here again about storage. Whenever I have the sun, but I don't need this water, I can store it, let's say, in a tank. Okay, so this storage can be by using also, if you want, well-insulated tank to not to preserve this heat and use it when needed. Or sometimes also you can store it using also phase change material. And you can place, let's say, in this tank some phase